All right. All right. Welcome everybody. I'm very new here. I'm from Oklahoma City. This is my first time to be here. My name is Aaron Krauss. I think there we go. That's me. I am a software engineer. I'm going to be talking today about Prolog. I like puns a lot, so it's Prolog, a prologue. If you're lucky, you're going to hear a lot more puns. That's just the beginning. So I'm Aaron Krauss. I'm a software engineer. I wanted to talk about Prolog because you probably heard the spiel, but I think it's a fantastic language that even if you don't use it, I doubt many people here, if any, do use it or will use it. It's so drastically different, and it's popular enough in the sense that it's something that you may have heard about. Kind of like, I compare it to in the era of like Fortran, COBOL. It's a little bit after that, but it's a classic language, and I think it's a really I don't know, I get excited about it, so you're going to get pumped up too with me. I'm going to make you get pumped up. So that's me. I'm Aaron Krauss. I am the code boss on a lot of the social medias. I don't do social media as much anymore, but I'm on Slack, the Techlahoma Slack, as the code boss. So if you want to chat with me there, I'm always there, like all the time. And I work for a company in Oklahoma City called Clever. I give quite a few talks in Oklahoma City, so I think everyone there knows Clever is, but I'm excited because I don't think anyone here does know who we are. So I'm sporting the Christmas sweater that we did this year. Clever is, we're a small company of 22, 23 people. We are a software development consultancy in Oklahoma City. So we've had some clients out of Tulsa before. We work with a lot of local clients. So we work with nationwide clients. So we build web applications, websites, mobile apps. So we do virtual reality and augmented reality. We build games. We have been working with a client on a trivia game that's released in the iOS store now. We do fun stuff. We've been around for about 10 years. In April, we'll be celebrating our 10-year anniversary. One of the reasons I get excited, too, is because we have various shirts that we've designed over the years, and I've got 3 of them here that I'm going to throw out if you can answer my questions. This is one of them. They're both shirt designs are from the OKC skyline. This is the Scissor Tail Bridge right here. I'll just go ahead and say this one's an extra large. I'll throw this one out first. The other 2 are larges, so if, whatever size you want, might hold off on your answer. That's about the least awkward way I can throw out shirts without explicitly asking for shirt sizes. So the first question is actually going to be coming here in a second. So that's Clever. We're spelled, instead of the second E, we're spelled with a Y if you want to Google us, but you'll see that at the end as well. The first question is going to be this thing. So I'm also part of this thing. Who can tell me what this is? What it is? What was that? No. It is a business. It is something. It is a logo for something. You got the first word right. I'll say that. Here we go. Code.org. All right. I'm just going to throw this one somewhere back there. There it is. That's I speak at classrooms. So Code.org is a program where, as software engineers, we can volunteer, and it's for kind of educational purposes. The point of it is for students who are usually teachers who teach K through 12. If they want to have a software engineer or anyone really in the tech world come talk to their students about anything, help out with the hour of code, etc. They're the company that runs the hour of code, if you have heard of it, and runs a loose term. They create tutorials and they encourage everyone to run it. So I'm a volunteer for them. If you want to volunteer as well, it's really cool. I've been contacted twice over the last year and a half, so it's not an everyday type thing. I went to speak to a couple classes. It's been fun. One of them was a 4th grade class, which is pretty cool to see students that early getting into it. But here's where you can volunteer, and that's all I'm going to give for spiels. Let's get to the meat of this talk now. So what is Prolog? It's a lot of things, but what it is, and we're going to dig into this. Usually, we're going to dig into this more, but what I should say is what it's not. It is not a web dev language. So what are we doing here at Tulsa Web Devs talking about Prolog, not a web dev language? Well, I think I've given my spiel enough already. I think it's just a cool language that shows you another side of programming that you probably haven't seen before. You might have, and we'll get into the language you might have used that's similar to it here in a bit, but it's most of the time, you don't think of development the same way you do when you're developing with Prolog. So Prolog is what's called a logical programming language. I really don't know of any other logical programming languages other than Prolog. And in fact, it's so tied to the language itself that, well, here's a definition. Let's get that out of the way first. What is a logical programming language? It's a set of sentences in logical form expressing facts and rules about some problem domain. There's 2 key words to remember that I'm going to pound into you, and it's facts and rules, because those are 2 of the 3 things that Prolog can do. Prolog can't, and there we go. Somehow that got out. 2 out of the 3 things. Like Prolog is a super simple language, and that's why I'm gonna like show you everything it can do with this talk. Prolog actually stands for programming and logic. Like that's part of the name, and it is a mind-blowing thing. But it's also a declarative language. This is where the fun part comes in. So to describe what a declarative language is, we first have to talk about what the opposite of that is, which is an imperative language. So that's shirt number 2. This is so you got the only skyline or scissortail bridge shirt. I now have 2 shirts of the Wheeler district area. We got the Ferris wheel a couple years ago. This is the skyline of that. So large shirt of this. Who can tell me what an imperative language is? Or best guess. Okay, we'll hold on to that. Okay, yeah.
A language is translating code into machine instructions directly.
Exactly. And I'm just gonna, I know there's a camera right there, so we'll just somehow that's gonna get there. All right, boom, second trick given. Yes, that's correct. So it's where you tell your compiler or interpreter exactly what you want it to do, which sounds like the most ridiculous definition because, well, again, I got some languages here that are imperative. They're languages that you probably have heard about, certainly have heard about. They're languages you probably use on a day-to-day basis. Java, JavaScript, Ruby, etc. Very common language. Top 10 languages right here. Part of the top 10 languages. But isn't that how all programming works? And before I ever was introduced to Prolog, I would have probably said, I think that sounds like a base enough definition to where I would say yes. But that's not always the case. So that's kind of where we enter into declarative languages. So last shirt, who wants to have, and I think I may have given the definition earlier, but who wants to do best guess of what declarative language is? I can hold on to this one, hold on to the shirt till later, that's okay. Okay, so declarative language is the opposite of that. It is a language where instead of telling your compiler or interpreter what you want it to do, you're giving it instructions on what to do. I'm sorry, not instructions, you're describing the problem. So, exactly, that right there. So, that's how Prolog works. It's a declarative language, and it's a logical language. So, getting deeper into Prolog has 3 things. It's got facts, rules, and queries. That's all it can do. It's got variables as well, but it doesn't have functions, which is, I think, a pretty mind-blowing thing. Like, there's no functions at all. The closest thing it has are rules, which are like functions that can only return true or false. We're going to get to all of this, I promise, really soon. So the way it works is you define a knowledge base using the first 2 things, facts and rules, and then you query data upon that. It's commonly used for natural language processing, and this machine right here, so this is Watson right here. Man, that would have been a good question. This is Watson. So Watson is largely built in Java and C++, but about 10% of it's built in Prolog, and it's that natural language processing piece. So whenever it's trying to figure out a sentence, etc., and this is old Watson. I'm not necessarily talking about the new API Watson. It may still use Prolog, but as far as mid 2000s beating Ken Jennings Watson, about 10% of that was written in Prolog. So real world uses of Prolog. So the big claim to fame for Prolog, and after this we're going to get into some code, is if you ever look at a Prolog tutorial, it's, usually the title will be, write a Sudoku solver in like 20 lines or something. Things that imperative languages would find great difficulty doing. You can do it, and I'm not talking like just validate that it worked. Like I'm talking like you get this set of inputs here, like a 2-dimensional array of 9 by 9 items, and you tell your program to solve this thing, like figure out what solution works with this. You can do it in imperative language for sure, but the way Prolog would handle it is it's magical, it's beautiful, and that's where it really shines. So solving problems like these where you can describe the rules, we can say that all rows have to add up to, all rows have to have unique numbers 1 to 9, all columns have to have unique numbers 1 to 9, and all squares as well. That's where Prolog shines, and we're gonna, at the very end of this presentation, I'm gonna show you a 15-line solution to solving a 9 by 9 Sudoku problem. It's really cool, it's really powerful. So before we get to all that though, let's do a little demo about how Prolog actually works. Feel free to ask me any questions along the way, and I want this to be interactive because that's the kind of guy I am. So all these scripts I'm gonna have to get input from, or else I'm just gonna make up some stuff. So I've got 4 little fun examples here. These are fun because these are my requesting user input from you all. The examples here are just normal, not requesting user input, so we won't dig into those. But let's dig into just a basic Prolog script. So if you see these 4 underscores, that's me going to get input from you. So this top line right here, before I get any input, is what's called a fact in Prolog. So this is likes is something that could be anything. We're just saying that Aaron, that's me, likes tea. So this right here, this likes is what's called a predicate. And it's accepting 2 arguments, Aaron and t. So argument, we're still using the same word argument as far as functions go, so you're probably familiar with that. We're saying Aaron likes tea. Okay, does anyone else here like tea? All right, what's your name, if that's can I ask? Patrick. All right, so Patrick likes tea. Did I spell that right?
You tricked me, guys. He's going to do it to you, too.
Yep. Who likes coffee? All right, what's your name? Blixa. Boom, there we go. Okay, like this. I like this user input. We got more of this coming up, don't worry. Okay, so Patrick also likes tea. Blixa, however, likes coffee. It's okay, we won't judge. But these are 3 facts right here. Again, we're building what's called our knowledge base. Knowledge bases are built up of facts and rules. These are 3 facts right here. Facts can have any number of arguments. They can have 1 argument, doesn't matter. We're just stating a fact. You'll also notice that every Prolog line ends with period here. This right here is probably the unique thing. This is what's called a rule. So this is how we can kind of get a little bit more logic. And this is about any logic you're going to have in Prolog will always be in a rule like this. So what we're saying here, we're defining a rule called friend. It's a predicate of friend. And it's accepting 2 arguments, x and y. If you ever see this thing right here, it doesn't mean equals. It means is true if. You're going to see an equal sign later on. But we're saying this is true if, and this is where we're getting crazy. We're saying if some x likes the same z, that another y likes that same z. So, and this is the whole like Prolog script right here. I'm going to try to run everything in this bottom area. If this gets too, in fact, let me just move that up a little bit because I think we're going to run out of space. So to run Prolog, there's various implementations of Prolog. The most common one is called SWI Prolog. So when you see me type SWIPL, that's what that is. It's SWI Prolog. And we're going to hop into the scripts directory first. And that's just going to load up the script. So we're in our environment here. So let's just see what happens. Let's see. Does Aaron like tea? And again, rules can only return with true or false. So Aaron likes tea. Let's see. Does Blixa like tea? What do we think it's going to say? No, Blixa does not like tea. So those are probably the easy ones. Let me hop up there to make sure we can see the whole script. Now, let's do the fun one. Let's do the rule. Let's see if Aaron and Patrick are friends. We're friends. We got it. We're friends. Let's see if, and again, I think you know what's coming next. Let's see if Patrick and Blixa are friends, and it's not. So, again, we're querying our rule base, our knowledge base here, just based on a couple facts and a rule. And again, so Prolog uses this, the way this works here, this X, Y, Z mapping. Anything in Prolog that is capitalized is a variable. Prolog will try to match that to some value. It's different than how this works in other languages. So other languages, when you're mapping a variable, you're saying X equals this. That's called assignment. You're saying X is equal to this thing. Prolog doesn't usually have assignment. Prolog has what's called unification. And you're going to hear me just bulldoze this word over and over again. Unification is how it works in Prolog. So instead of saying that X equals this thing, Y equals this thing, this is the declarative part of Prolog. Prolog is figuring out what represents this rule. How can I make this rule true? So because X and Y are variables, it's going to try to map those to something. If you do a non-capitalized thing, it's called an atom. So these right here are actually atoms, and those are just constants. Atoms, you probably heard that in other languages as well. Another cool thing we can do here, and we're going to get to a more complicated example here in a minute. If we wanted to say, let's just see who likes tea, we can put a variable in for that first thing and just say tea, and Prolog is going to say, nope, didn't like that. No, I was trying to see let's see if I try. I didn't actually test. Okay, we're gonna do a better demo in a minute then. Failed demo. Okay. Yeah, I wanted it to return Aaron and Patrick. It would return both of those. Um, it should have, yeah. The rule should work for both of them. So this is an on the fly demo. This is one that I actually have done. So we'll mess with this one. Moving on to the next thing. Same thing, but a little bit more complicated. We've got a rule at the bottom, and I'm gonna go ahead and exit out of this. We've got a rule at the bottom here called food flavor, and we're saying we're kind of doing the same thing, but we're combining two different types of facts. We're saying we've got X amount of food types here, so you can tell I'm going to ask for some input here. So be thinking of various types of cheeses, meats, sodas, and desserts, because that's coming in about 30 seconds. We're mapping them to flavors, then we're going to say what kind of food flavor, what type of food, such that it's the same type, maps with this flavor, such that it's the same type. So, all right, user input time. Who can tell me a type of cheese? Just throw them out there. Gouda. There we go. I need another one. Provolone. There we go. The old sandwich cheese. All right, let's get a meat. What do we have here? What was it? I want to say I heard ham, so we're gonna go with that. Soda. All right, I heard Pepsi first. Last one, dessert. Cheesecake. All right, save that. Let's run this script now. Okay, so we've got various food types here, various flavors. So if we wanted to check, so let's look at this rule. We've got a food flavor, so we've got X and Y. So we want to map basically such that this food is of this type, if you will, and then it's got a flavor for this type. So how are we going to match a food with a flavor? So let's see what happens if I map Gouda to a type of dessert. What are we going to get? We're going to get false, because Gouda is, according to this, Gouda is a cheese, and a cheese is savory. Ooh, interestingly, we had a turn of the twist here. A cheesecake is a dessert, and that's not going to be savory. That's going to be sweet, which makes sense. Let's make sure that works. Whoops, that's not what I meant to do, is it? Let's see. Oh, I didn't want to check that. I want to check to see if cheesecake is sweet. And it is. Okay, I think that was what I meant to check the first time. So you can see we're kind of combining various fact types when we're checking rules, and that works completely fine. What these are called, so this whole thing is a rule. This is our predicate right here. Each one of these, up to the comma here, is what's called a subgoal. For a Prolog rule to return true, each subgoal has to be true. So food type has to be true. It has to map to some X here, such that some Z maps to a some Y with the same Z right here. So again, this is unification. Prolog is figuring this out. So this is where I tried this out earlier. Let's say we wanted to find whatever desserts are, whatever food types are sweet. So I'm going to say what, because that's the variable I always use. So again, it's capitalized, so we're setting that to a variable. So if we say what food types are sweet, there we go. That's what I intended to happen before. So we're saying, maybe it's because I was trying to map it to variables that I was using in the script. I bet that's what was going on. So we're saying Pepsi is sweet. We can go on, and cheesecake is sweet. So we can iterate through what is sweet. If we put in something that doesn't work at all, like let's just say sour, it's just going to say false. Nothing mapped to sour at all. We can go the other way around too. Let's say that we had, Pepsi. What does Pepsi map to? Pepsi's sweet, and that's it. So you can see this is unification and Prolog. It's not assignment. It looks like we're just saying these variables are these things, but that's the imperative aspect of it. That's us telling the program this is how it's going to work. This is Prolog, and unification is Prolog's way of mapping that for us. Again, we're not telling it how to do this. We could look up the algorithms as to how Prolog's doing all this, but that's not the point of declarative programming. It just handles it. Now, if this paradigm seems completely new, and I think it probably does to a lot of people, there's a good chance you've actually been using a language that uses declarative programming before, and that's, anyone want to guess another language that uses? SQL, there we go. All right, who said it first? We got a shirt here. All right. Hey, we got it. We did it. Okay, last shirt. If anybody, if any shirt sizes are wrong, or if anybody wants another shirt, if you happen to be in OKC, I'd be happy to get you one. We're just in the Midtown area. So SQL is, yeah, probably the biggest declarative language that you have either heard of or used, but it functions the same way. You're not telling it, when you query something with a select statement, you're not telling it how you want it to query the data. You're just giving it rules. You're saying, I want these 3 columns from this table. I want it ordered in this manner. I only want things where this value is higher than 5, etc. You're not telling it what to do. You're describing the problem you're trying to solve. So the next time you run a SQL query, just think you're doing declarative programming. Give yourself a pat on the back. Okay, next demo. And we're not just going to talk more about rules, and well, we are going to be talking about rules and facts, because that's all there is in Prolog besides a query. I haven't really mentioned the query, but that's what we were doing down here. I'm sure many of you picked up on that, but this is the third part of Prolog, this query. Whenever we're running a Prolog script and we query data off of it, that's the query. How many more times can I say query? Okay, here is kind of a small example. No user input needed on this one because it's kind of a unique case, but by default, we have been just passing in atoms to Prolog and letting it unify whatever we need to do, and that's what we're still doing here, but let's look at what's going on here. We've got 2 facts, which are saying that a lion is a cat and a tiger is a cat, so proof that you can have various arities when you're defining a fact, arity being the number of arguments you're passing in. So we're just passing in a single argument here. We've got a rule called Dorothy, and we're saying that there's 3 variables, x, y, and z, but Prolog is what it's doing. It's saying is true if x equals lion, y equals tiger, and z equals bear. So we are unifying. This might be the first time we've seen the equal symbol. It's still unification with the equal symbol, but Prolog is handling all the unification automatically. It doesn't need input from us. So if we exit out of this, let's load that third script. So if we say Dorothy with lion, tiger, bear, we're going to get true. If we say anything else, it's cat, it's going to get false. So, and what we can do as well, we can say, just like we've done before, Prolog is going to unify that to lion. So, simple thing there. And then we've just got a second rule here, twin cats, where we're saying that we're proving that it's okay to query the same fact in the same manner, and it's just going to unify it to 2 different values, such that they're different. So if we say, and actually they might work if they're the same too. Let's try it. So we're saying they are twin cats. Let's see if we can do just lion and lion. Okay, so that works as well. But if we try to do something that it's not mapping to, it's going to fail, such as a bear. Okay, little simple example here. The next one is a fun one, and this is going to be the last of our simple examples, and we'll do a little bit more and then dig into how we can actually solve Sudoku. It's like how do you draw an owl? Here's the draw a couple circles, then draw the rest of the owl. That's what we're going to do. Okay. User input time. Okay, so I need someone's information, and then either make up a dad's name, or you can give me your real dad's name, whatever you're comfortable with, and then fake or real grandpa's name, anything. But anyone wanna volunteer for this one? Fake names are totally cool too. John. Okay. John. What's the next fake one? Paul. Okay. Okay, and that's not how you spell Paul. And we're gonna use this one twice. Okay. Last one. Test. What was it? Test? All right, we're gonna do it. Okay. So we just defined some facts here, and what we're saying is, oh, whoops! I think I did these wrong. So I was trying to say John is the father of Paul. No, I think that's correct. And then Paul is the father of Test, such that John is the father of Paul. I think. Oh boy, let me just make sure I got the order of this correct. Hop over to my reel. Then, okay, Zeb, John, Boissini, John. Okay, we got it right. Boom. Okay. So John's the father of Paul. Paul's the father of Tess. Good. Man, it's all this recursion stuff. Hint, hint. That's what we're going to get into. Messes with my head sometimes. So we're going to talk about recursion in Prolog. Prolog, while it's not a functional language, it's declarative, and a lot of functional languages are declarative as well. And not necessarily with that paradigm, but associated with that paradigm is kind of a lack of looping, if you will. There's no for loops in Prolog. There's no while loops. A lot of functional programming languages share that same idea. So how do you handle the idea of looping? Because you need it somehow. Well, that's where you come into recursion. So recursion being the idea of calling the same chunk of code over and over again and then exiting on some base case. That's what we have here. In Prolog, the way we handle recursion is we have two rules that are the exact same arity and everything, and that's completely fine. This is different from most programming where you would have a function with the same arity that usually doesn't fly because you don't know which one you're going to call. Prolog, it completely flies because the way it works is, let's say we call ancestor x and y, which we're going to do in a minute. If this first rule fails, and it just goes down the script. If this first rule fails, it just checks for the next one. So the way a rule works in Prolog, each of the sub-goals have to be true for a rule to be true, but as long as one rule returns true, then that you're calling, then it's fine. Like we can have 10 more of these ancestor x, y's with various sub-goals in them, but as long as one of them, doesn't matter which one, returns true, then the whole statement returns true. So let's take a look at how this works, and I'm just going to exit out of this. We'll load our last fun example here. So the way this works up here, we've got our first rule, which is our base case. It's saying ancestor for x and y is true if just father of x and y. Like that's it. So for example, if we pass in, we say ancestor John Paul, that's going to be true. And it's just going to hit this first base case. We didn't have to do anything recursion based. Let's say this returns false though, such as if we were to pass in John and test, for example. This is going to fail because John and test they're not directly related with the same fact. So this rule is going to return false. We go to the next rule and we say ancestor x and y, and we say we're doing a father query here. We're saying if father of some x, so the first thing that would be John. If father John and then some z, see that's not something we passed in, so Prolog's going to unify that. We don't know what the z is going to be, but we can assume it's going to be one of those three values. So if that some z works if ancestor z is the father of y. So y is test. That's the one we would have passed in. So and we'll walk through this again, but just to show that that works. That's true. So the way that worked is we tried to hit the base case. It failed because there's no direct fact here. We hit here. We don't know what Prolog unified z to, but we know x is John. We know that y is going to be test. So we say ancestor is going to get called again. This is that recursion part. So some z, again, we don't know what it mapped to, but we can assume it's going to be Paul. So let's say ancestor, what we assume is going to be Paul, comma, test, is going to get called again. So the recursion piece of this is going to call all of this one more time, and we're going to hit this first rule up here. So we're saying ancestor of what we assume is Paul and test would be father, Paul and test. Well, that's true. So that's going to return true. And then that returns here true. So this whole sub-goal returns true. And then we found out that, so our z at this point was Paul. So we found out that because John is the father of Paul and that Paul is an ancestor of this other person we're trying to check for, it all works. So we got true for the first sub-goal, true for the second, and bam, it all passes. So that's why we're able to say John is a ancestor of test. We could go, as far down as we want to go. Let's just say Foo is the father of, let's say test is the father of Foo. We just want to say is that now we're going to have to reload the script here. Got to reload the knowledge base. Ancestor John is the ancestor of Foo, and it works. Now, with recursion, you oftentimes have to worry about a stack overflow. If you create too many frames, let's say you're going, 1,000 frames deep, that may not be a ton, but at some point you will probably hit a stack overflow. We could have 1 million or more. We could have 1 billion lines here. Now, I guess you're getting into editor constraints there, but we could have as many lines as you can feasibly have per father, just continuing to go down the answers path, and we're never going to run out of stack memory here. The reason for that is because Prolog, by default, handles what's called tail-optimized recursion, and a lot of languages do this. The language has to support it, but the way that works is if your recursive call is the last piece of logic, which it is here, then this program, Prolog, will make sure that there's a constant amount of memory that's maintained throughout this. So we could loop over and over again, doesn't matter, because all Prolog has to remember is, am I true, am I false? It doesn't have to think about what happens next in the 63rd frame of this when I start popping back up the chain. because again, this is the last thing. It knows there's nothing else, so all it has to remember is true or false, or whatever in any language, tail optimized recursion enabled. It just has to remember what the current state of everything is. This doesn't work if I were to swap ancestor with father here. So if ancestor is the first subgoal, we would still get the same results that we have now, but we're not tail optimized. We're not doing tail recursion optimization there because the recursive call is the first subgoal. There is logic after that, so Prolog has to actually track what that logic is in each stack frame. So we're using tail optimized recursion here. It's incredibly helpful. A lot of functional languages support this. A lot of, I think probably most. I don't want to say most because I'm not sure, but I think a lot of languages support this. And if you make use of it, it can really improve the speed and security of your program. Security meaning it's not going to blow up on you. So this is a big thing that we just covered. That's it for the little examples, except that I want to do just some basic query type stuff. So Prolog, we've seen some variables and we've seen some atoms, which is just constants. There's two more data types I'm going to talk about. One of them, which I'm really going to hit home a lot, and those are tuples and lists. So tuples in Prolog are, just an enumerable data type of, whatever you want. We're just going to say 1, 2, and 3. And just to prove that, this works, it probably looks silly, but that's true in Prolog. We have the same thing with lists. The difference with tuples and lists in Prolog being that tuples are fixed length. You can't add them once they're set. Lists are pretty dynamic in Prolog. So again, just doing the same thing here, proving that they're two different types. One of the nice things with lists are that we can bind each two variables. So if I wanted to say 1, 2, 3 equals ABC, that all works. And again, I want to show one more thing with unification that other languages would just scoff at and not be able to do. Let's say we want to do 1B3, and let's see if I can get this right. A2C. That works because this is not assignment. We're not setting one side equal to the other. It may look like we're doing that, but what we're doing is telling Prolog to unify all the variables that are there. It doesn't matter where they are. This is just Prolog saying, okay, B has to be this for this to be true. A and C have to be this. So this is lists with unification. There's one more very powerful thing I want to show with lists and Prolog, and that's going to be it as far as like what I want to show you. Then we'll do some Sudoku stuff, and it's that other languages can do this easily as well. But with Prolog, you can split lists. So if I want to do, let's just say head, pipe, tail. Again, they're capital, so that means they're variables. If I do this, head is going to equal the first item of the list. Tail is going to be the rest of the list. So it's still a list. It's just going to be, you're more or less popping off the top item, setting it to a variable. Tail is going to just be the remainder of the list. Now, we're going to get into some of the messy parts of Prolog right now. Let's say I have a list of, one more thing I want to show too is if you, there's an underscore character. It maps to a variable, but it's a wildcard and it just throws it away. So if we do this, again, I don't know if I've tested this, but this should it just dumps the underscore. So tail is 2, 3. We don't even care about the head anymore. So we're going to use the underscore later on. But let's say that we've got a list of 5 items in here. This is where we get into an area where you probably don't want to use Prolog. Let's say we wanted to access that third item there. Well, there's no sub index like most languages are going to have. So to do that, we've got to keep splitting it till we get to that third item, and then we dump the rest of it. So how do we do that? We're going to pop the first item off, put that into another split list. We're going to pop that first item off, put that into another split list, and then we're going to set that variable equal to, let's just say A. And then we're going to I can't even describe it anymore. So, okay, well, let's see if okay, there we go. We did it. Yeah, that's how we access the third index, second if you're counting from 0. This is not how you would use Prolog. This is big time code smell. But you can do it. This is how you would do it. So, one of the things I'm going to end with the takeaway is there are problems that you use Prolog to solve, and most problems you don't use Prolog to solve. If you have to do things like this, which are what you probably consider day-to-day operations, you don't use Prolog. But soon, right about now, we're going to get into some situations where you actually would want to use Prolog. So let me get out of this. We're going to talk about how you can use this to actually solve a Sudoku problem. So I'm going to go through the real Sudoku solvers that are like 15 lines long, which I'm going to show you at the end, I'm not going to dig through the code on those. I'll show it, but it's just, if you do anything in 15 lines worth anything, it's going to take you a while to parse through it. It's no point in really talking about it. I'll show it though. I've got another Sudoku script there that actually walks through how Prolog handles solving Sudoku, but instead of doing a normal 9x9 grid, we're going to do it simple. We're just going to do a 2x2 grid. It's not going to have these numbers, but this is the idea. It's a 2x2 grid. It's going to just be the same concepts apply, but it's just going to be much easier for us to look at the code. And that's the Sudoku script right here, and I'm going to full screen this whole pane. Okay, so we're at line 38 there, and this whole thing at the bottom is actually just the query that I'm going to issue to call it all. Okay, so looking at the whole code, and I'll just go through the code to show you that's not too long. And that's it. That's all the code. So let's solve Sudoku. We're going to solve a 2x2 Sudoku puzzle, and our grid that we're passing in is this right here. So we're passing in a 4x4 grid. It's just a list of 16 elements. So first 4 are going to be row 1, second 4 are going to be row 2, etc. The only numbers we have for sure are 2 and 3 up in the top right corner, 3 and 4 in the bottom corner. We're going to ask Sudoku to solve this. So how do we do this? Well, let's think about this. We've got a rule here that's going to pass in puzzle. We're going to set puzzle. That's what we're passing in, blank puzzle. And solution is going to be the unified completed puzzle. It's going to be our list of 16 elements that's completely solved. You can see we use all the wildcard characters down here because at this point we don't care about them. They're just placeholders. So we're initially setting solution equal to puzzle, which is just the unsolved puzzle. Then we're unifying puzzle to 16 variables right here. Just a list. That's just another way you can unify multiple variables at once. We're just saying that puzzle is a list of these 16 variables, square 1, 1, square 1, 2, etc. This little line right here is a rule that comes shipped with Prolog. It's just a way to say that every value of puzzle needs to be between 1 and 4. And then the next 12-ish lines, not including white space, are just us mapping what does row 1 mean, what does row 2 mean. So we're just setting more variables. So row 1 is just, whoops, that's not what I meant. Row 1 is a square 1, square 1, 1, square 1, 2, 1, 3, 1, 4, etc. Goes all the way down to row 4. Column 1, 1, 1, 2, 1, 3, 1, 4, 1, etc. Square 1 is going to be that, this right here. We're just mapping variables. That's all we've done so far. So we've spent 23 lines mapping variables. Let's actually get to the core of everything, and that's literally this right here. That's all the logic there is. So we're calling this rule called valid, and we're passing in a list of our 16. I'm sorry, this is the list of 12 variables. We're passing in all of our rows, and we're going to use what we just learned. We're going to use splitting lists, and we're going to use recursion to check to see how this works. And I want to reiterate, we're not validating that this Sudoku solution is valid. We're saying figure out what the actual solution is. So in 7 lines of code here, more or less, we're solving a Sudoku puzzle. We're not just saying here's a solution, see if it's good or not. We're saying solve it. So we're passing in row 1. Let's just start off with that. I'm sorry, we're passing in the whole list. Well, this first rule here is actually not even a rule, it's just a fact. And we're just saying that an empty list is valid. Well, what we're passing in is not an empty list, so this fails. So we go to this rule right here, where we automatically split head and tail. So head is going to be the first item of the list we're passing in. It's that row 1. Tail is going to be the rest of it. And here's another function that just comes shipped with Prolog, and it's just saying, verifying that everything in this list, which is row 1 is still a list, let's make sure they're all different. So everything in here is all different after this line. We're just verifying that everything's all different. And then we just pass the rest of the list back into valid. So this is that tail optimized recursion again. So the rest of the list is going to be row 2, row 3, 4, column 1 through 4, squares 1 through 4. And it's getting passed back into here. Well, it's not an empty list still, so that's going to fail. So then we come back to the rule. Well, head, and when we pop off the first element, it's going to be row 2. So we just kind of keep doing this over and over again. All we're doing here is saying everything has to be different in row 2, and then just pass it back in. So we're literally just saying everything has to be different. And then at some point in time, when we've done this 12 times, we will return an empty list because tail will be empty. That's going to return here, and that's going to be false. I'm sorry, that's going to be true, and that exits the whole thing. So I've done a lot of talking. I commented this out because this is just the query. I'm going to uncomment this and copy that. Let's open that back up again. Let's hop out of there because I'm not in that directory anymore. Okay, so we've got Sudoku loaded. I'm just going to paste that, and I'm going to full screen this because that's a little bit too small to see there. Now, my paste looked very strange. But by default, Prolog tried to map solution. And it did so successfully, but by default, Prolog, the SWI Prolog, I assume query runner, just limits a number of lists to something. So if we want to actually prove that it did the real thing, I think it's some weird thing like this we have to do. There we go. Prolog's got some quirks, and at least the query runner does here. But it solved it the whole time. It just, the view right here didn't want to spit everything out. So we've got our full solved Sudoku puzzle. It's not written very nicely here, but we can see 4, 1, 2, 3 is the top row, 2, 3, 4, 1 is the second row, 1, 2, 3, 4 is the third row, 3, 4, 1, 2 is the last one. And this is a working Sudoku solution. So this is, I don't know how magical this feels, but if you think about how you actually would have to solve this in an imperative language, all we had to do was tell Prolog, we need these to all be different. That's not what I meant to do. We need all of these things to be different, everything in these rows to be different, and all the columns to be different, and that's it. Like you can't do that in imperative programming, the same way you can here. You could write, I guess, a function that was all different that does all this, but I guarantee you all Prolog is doing underneath the scenes is just saying, this can't equal the same thing as these 3 things. So these ideas can't be used in imperative programming the same way that they can be in declarative programming. So that's the demos that we're going to go through. The last things that I want to show are just how would you solve an actual Sudoku puzzle, the 9 by 9 thing. So this is that script I was talking about. Again, all this commented out stuff is stuff that I'm going to run. This is the whole program right here. I'm not going to go through it because honestly, I don't think I understand a chunk of what's going on there anyway. But we're looking at 15 lines of code, and that's one of them is a white space. So really 14 lines here. And here at the bottom, we're going to pass in. I am going to uncomment this. That's going to be part of it, just because I don't want to have to type that out in a query. I'd rather just run this thing right here. And this map list at the end. So basically, we've got our problem here that we're calling this rule. That's just getting our empty puzzle, so I don't have to type it out in the query. Sudoku is actually what's going to solve it. This is this first rule up top. And then map list just makes it pretty print. That's it. So if we want to do this, let's go ahead and load. Let's load that. Whoops, we're in demos. And after this, I've just got one tiny thing, and then we're done. So we got loaded. All right, let's print that out. I'm going to full screen this, and bam. The reason this is all pretty printed there is because we use that map list at the very end. Otherwise, you can see Prolog still unifies our solution to what we saw before. But we just solved a Sudoku problem there with more or less 14 lines of code. And just to show what that was at the beginning, you can kind of see it right up top there. So a bunch of wildcard characters. We had some constraints in there, but that's it. Like we solved Sudoku. And to do this in Prolog, if we had a 16 by 16 grid, we could do it just as easily. If you did this in an imperative language, you're exponentially increasing logic there. So these are the things that Prolog is very good at, but I said it's not used for web development, and that is mostly true, but we can actually create a web server in Prolog, and I think this is just one of those things where you're like, why does this exist? But it exists. We can use Prolog as a web server. It has modules. I don't know how they fit into the whole rule ecosystem, how they work, but they work. So if I run this script, which we're going to do, it's going to create a server on whatever port I pass in, and it's got a handler that's going to say hi, and say hi returns back hello world. And let's see what that does. So server started at localhost 2000. Let's check it out. And there we go. Hello world. So you can use Prolog for, smart things, and you can use Prolog for ridiculous things. But I'm sure there's a valid reason to use it as a web server. So here we are, Tulsa Web Devs. Next breakout, let's do some Prolog server stuff. That's a joke. So that's all I've got. I hope I kind of opened up your mind just a little bit to how another language would handle a problem that you might not handle the same way. And the way it handles it is by saying, please let me take this work away from you. You just have to describe it properly. So the big takeaway, which I kind of alluded to earlier, is Prolog is really powerful when using the right solution, figuring out problems that require a ton of logic in the sense, but are described really easily. So think about tic-tac-toe, various types of games that behave in such manner, Prolog can handle that like a charm. And you can do it in imperative languages, but it's just not going to be the same. You're going to have to tell all the logic instead of just describing the rules. But Prolog is silly when used in the wrong situation. So we kind of looked at how we would get an X item of a list. Those are kind of things that are probably things you don't do. And that, there's a whole suite of programming that you just wouldn't do with Prolog. But there's a right time and a wrong time. So that responsibility is yours. So part of the reason I wanted to give this talk is because a few years ago I read this book by the pragmatic programmers called 7 Languages in 7 Weeks, and Prolog is one of those. There's a bunch of languages, 7 to be exact. You got Ruby, Scala, a bunch of functional ones, Scala, Erlang, Haskell. It has a prototypal language called IO, which if you ever wondered how JavaScript actually functions under the hood, it's a prototypal language. IO is a true prototypal language, and it's really cool to see how that actually works. JavaScript's kind of pure IO, kind of true prototypal, kind of not. It's not moving in that direction, but it's at its core, it is still prototypal. So anyway, I'm digressing. This book was awesome, and it's how I got into Prolog, and I think the language itself is pretty bomb. So that's me. I'm the code boss. I've got a website called thesociety.org. That's my blog and main page. There's also a blog as to why it's named that, because there's a story. That's my company, Clever. I told you we spelled it weird. If you want to learn more about what we do, again, we're a software development consultancy in Oklahoma City. We're clever.com, and if you want a shirt and you're in OKC, please stop by or hit me up on Techlahoma, and you can come and drop by. And the last thing is I know this is getting streamed, which is awesome, but if you ever want to just go through all of what we did with words, just old pen and paper, but electronic pen and paper, I've got a blog, and I've blogged about this whole thing in 3 kind of parts here, where the examples are the same, but the names are different. But you go through everything that we just talked about here, literally verbatim. So if you have any interest in kind of just reading everything we did, I've got a blog post, just thesociety.org/blog, and that is it. Any questions? Yes.
So how do you measure the performance of a Prolog program or a declarative program? Because like in SQL, you have SQL explain plans, right?
Mm-hmm.
But let's say in your ancestor example, you accidentally flip the terms around so it wasn't tail recursive. How do you know that you did it wrong?
I've got 3 things to say. One of them, I'm not a Prolog expert. 2, I'm very comfortable saying I don't know, and that's kind of the answer here. But the real answer that I want to give is just if you notice it being slow, if it blows up, then that's bad. Thank you. I'm terrible at repeating the question. So the question was, how can you measure performance in Prolog? Such an example was tail optimized recursion. How do you know that it's working versus not working? The core answer is I don't know for sure. But that's my real answer would just be, do you notice anything? Yes.
Does Prolog support mutual tail call elimination if you're doing mutual recursion?
I don't. So does Prolog support mutual tail call recursion? I don't know what that is.
Okay.
There we go. Let's just say yes. No, I don't know.
What do you use Prolog at work or for like use cases that you've found useful?
So at work, I have not been able to find use case where we build mostly web applications. There are. So that's being said, though, we've talked about. So we do a chunk of natural language processing, and we use libraries in Python for that right now. But I have brought this up to my coworkers before about putting using like a queue like RabbitMQ or something, and dumping data there, and then having Prolog watch the queue and actually picking up that and actually running some natural language processing logic based off of that. We haven't done it yet, but that would be the big thing that I would want to do, because in my mind Prolog fits that perfectly. You can break apart a sentence. You can say what's a verb, what's a subject, how is this used. If you wanted to do something custom, that's an area where I see Prolog really shining. So, not yet, but that's. I forgot to repeat the question. Question was, do I use Prolog in my day-to-day or at work at all? No, but those are kind of some ideas that I'm planning on us either implementing at work or genuinely talking about doing, which we've talked about it for sure. Good question.
How
Yes.
do you get obviously you're typing it in for the demos here,
Mm-hmm.
but if you were to use it at work, what would you do to get information into and out of the interpreter besides just...
You know, the question is, how do we get data into Prolog? There is a way to pull, so you define your knowledge base in, various scripts, and there is a way to pull that in from other scripts. You're just importing libraries. That would be the prime way that I would do it at this point. Yeah. Otherwise, you could certainly serialize it and store it in, like a database, and then pull that out and prologify it, if you will, turn it into an actual knowledge base that Prolog knows how to handle. But at this point, I would say just import other files. And it depends on your use case. Cool, awesome. Well, I completely mean that I'm not a Prolog expert. I just thought this was, I've gone through this, many times. I've gotten a little bit deeper than this in the Prolog world, but I got to a point where I was like, I need to tell people about this. This is awesome. So we're kind of at that point. So that is it. Then thank you very much.